Hello, my lovely students. So here we are finishing up section 2.2. So this introduces sine and cosine, and we're looking at the first quadrant of the unit circle. This is the quadrant that would be best if you're very familiar with. It's like making flashcards where it's just like pi over 6 is what in degrees? 30. Pi over 4 is 45 degrees. Like having the radian to degree measure and then knowing the cosine of those and the sine of those. All the rest we can derive from sine and cosine, but if you know those sines and cosines, it makes it a lot faster. This quadrant, you can then copy into the other three, and you just have to remember what's positive and what's negative, which I do by drawing a little triangle in whatever quadrant and then just seeing, well, which way did I go? We'll see that as we continue on. But in here, I wanted to show you where these three triangles fit in here. So our 30, 60, 90 fits in right here at the pi over 6. So remember up here, this is pi over 2, which is 90 degrees. And then if I divide that by 3, I get pi over 6. 90 divided by 3 is 30 degrees. And then if I doubled that, 2 pi over 6 is the same as pi over 3, so this is our 60 degrees. And then half of pi over 2 is pi over 4, half of 90 is 45. So those angle measures there that I wrote, those correspond to the angles here. So even though we're in a unit circle and technically the distance along the edge of the circle is the same as the angle measure, like when you're looking at these, you want to think of them as angles. So our 30 degrees here, if I take that point on the unit circle and drop my height down, I now have a triangle. And that is this triangle. Since we know our radius is 1 because it's a unit circle, then we know the x and y coordinates now. So we go over the long side on the 30, 60, 90 is the uglier one. Square root of 3 over 2. The short side is the prettier one, 1/2. All right, now our 45, 45, 90. If I drop that vertical right there, then we can see to get up there, square root of 2 over 2 and square root of 2 over 2. And now our 60 degrees. So I took the 30-degree triangle and like recopied it around, but the picture looks a little weird. So let's just like go back in and fix this. But there's our long side is square root of 3 over 2. And then our short side down here is 1/2. So we go over the short side 1/2 and then up the long side square root of 3 over 2. So I want you to look at the x and y values here, and I'm going to add in 2 more points. So right here, that is over 1 unit on the unit circle, and then no up or down. And then up here, this is no left or right, and then 1 unit up or down. So if you look at these 5 points organized like this, you can see the x values start at 1 and run up to 0. The y values start at 0 and run up to 1. So in our first quadrant, the cosine values are the x's. So cosine starts at 1 at a 0-degree angle and then goes down to 0 for the 90-degree angle. Sine starts at 0 and goes all the way up to 1. So you just want to be comfortable knowing which one is which. And for me, I'm always thinking about where is the triangle, which side's the long side, which side's the short side for my pi over 6 versus pi over 3. Because it's really easy to get those backwards. Like the big one is pi over 6, like your gut wants to say 60 degrees. But you have to remember a sixth of a pi is smaller than a third of a pi. So the 30 degrees goes with the smaller fraction, the pi over 6. All right. And then you can also see it's like 1, 2, 3, and 3, 2, 1. Like you can even kind of continue that pattern, like square root of 1 is 1. So square root of 0 is 0. Up top here, instead of square root of 3, square root of 4 is 2. And the divide by 2 would be 1. Square root of 0 divided by 2 is 0. So there is actually a consistent pattern that occurs here. So I just wanted to kind of explain how I view the unit circle and that I am always looking at those triangles. Where's the triangle? What direction do the sides go in? When we get to some of the application problems in the next chapter, we're going to kind of ignore negative side lengths. But for the unit circle itself, like we need those values. All right, so the range of sine and cosine. So think about our unit circle if I go all the way around it. One, 0, 0, 1, negative 1, 0, and 0, negative 1. So my x values go 1, 0, negative 1, 0, and back to 1. So if I was going to plot just those points, we start at 1, we go to 0, we go to negative 1, go to 0, we go to 1. This is cosine. And we're going to see the actual graph has a little more curve to it. But that's our first 0 to 2 pi or 0 to 360 degrees of cosine. All right, so the range of this function. So I'm just taking all of my x values and I'm plotting them with whatever angle value I'm putting in and then the x value on the unit circle. That's how the function gets produced. What we want to look at is our high and our lows. So our high values and our low values. If we look on the unit circle, there's our high value, there's our low value. So the range on cosine is from -1 to 1 inclusive. So the cosine function of just some angle will always produce either -1, 1, could be 0, or any fraction between those. But we're never going to get something bigger than 1 or something more negative than -1. Unless we have extra numbers inside doing crazy stuff. Now let's take a look at the sine. So our sine actually starts at 0, goes up to 1, 0, -1, 0. So let's just take a quick sketch of that. So 0, then up 1, then 0, and then down 1, and then 0. All right, and there's a rough sketch in, so it's more of a curve. It's not just, straight lines connecting the dots. But we see here, same thing. My range for the sine function is the same, -1 to 1. And in fact, if you look, Like the graphs are looking pretty similar. Like instead of starting here at 0, 0, if I started up here at this 1 point and went down, and remember these functions continue. This is just one period, one collection of unique points, and then after that, we get the same pattern, same pattern, same pattern, same pattern, same pattern. And that's because in the unit circle, every time we go 360 degrees, well, now we're tracing the circle again. Now, some people actually think like, all right, so look at my pen in the video. I'm tracing a circle. All right, I'm going to keep tracing the circle, but I'm going to move my pen. All right. And now you see how, to you guys, you're not seeing the forward and back motion so much, but you're seeing the up and down. Now, instead of drawing a circle, if I drew a spiral, so I keep turning at the same rate, but now I move my pen forward, you should kind of see that up and down motion. So that's one of the ways to actually perceive a sine and a cosine graph is this is actually a spiral in space, and we're just superimposing two particular views onto that spiral. Now that's a very like esoteric, weird, out there kind of way to think, but I saw that early on in my math career and it actually made just a few things click. It just gave me an extra way to kind of consider the shapes and how they relate together. All right. But there's our two shapes. Now over here we have even or odd functions. All right. So these definitions are hiding somewhere in the book. Even functions are functions that can be divided in half the same way x squared, the basic x squared graph, can be divided in half. So it's reflective across the y-axis. So even odd functions are like x cubed. So they're not horizontal, they're not symmetric across the y-axis, they're not top-down symmetric across the x-axis. They're what we call rotationally symmetric. So if I take the entire graph and spin it 180 degrees, I get the same graph again. This is what the graph of x cubed does. Without any other numbers, just x cubed. Comes up, flattens out, goes back up. And if I spin the whole graph around the origin 180 degrees, all the points will line back up. So we call this a reflection about the origin. Now, if we think about those two concepts, we can write some function notation that pairs along with this. So my reflective across the y-axis, I'm taking like two different points. Here, we'll like this. And you imagine like between my two hands, that's my y-axis. So if I go over to my third finger or to the other third finger, like my x distance is either positive or negative. But to get up to that first knuckle joint, it's the same vertical distance. So these function values are going to be the same. Whether I plug in x or negative x, the height, where they go on the graph, will be identical. So the formulaic way we write this is we say f of negative x will equal f of x. Now, our rotationally symmetric are a little weird. So like our cubic graph goes to 1, 1. It also goes to -1, -1. So any point where I plug in x and I get f of x, Then the flip is when I plug in negative x, I want to get negative f of x. So f of negative x, hold on. So my normal, let me just draw that picture. So my normal point is x, f of x. And then for this to be an odd function, I need it to go back to negative x, and I need it to go down the same distance that this one went up. So that means this ordered pair is negative x comma, and I want the value to equal negative f of x. But anytime I write an ordered pair, whatever the input is, this also must be negative x comma f of negative x. So I want those 2 points to be the same. So that's why I'm getting f of negative x is the same as negative f of x. And this is god awful to listen to because the negatives are just moving all around, and it's really easy to trip the order up in your brain. So what we do with this equation needs to be true. Since we're assuming it is true, I can manipulate it some. The most common manipulation is to take this negative here, and I'm actually going to multiply both sides by a negative 1. So now we have negative 1 of f of negative x equals just f of x. And the only reason we do this is because we're generally presented with f of x. We can see what it is. So if I plug in a negative x and I see what I get there, if it's equal to the original function, we actually know we're even and we can stop because we don't have functions that are both even and odd. We can have graphs that are. A circle is both even and odd, but a circle is not a function. And then if those don't equal, then we do negative 1 times the whole thing and see if that gets us back to the original function. And if it doesn't, then we just say it's not even or odd. The only reason we're even talking about this is our sine and cosine, and then because of that, all the other trig functions can be classified as even or odd. They fit one or the other definition. So with our sine of x, so let's kind of pause, put the even and odd to the side for a second. Just look at our 2 unit circles here, and I want you to think like, when is the sine going to be positive versus negative? When is the cosine going to be positive versus negative? So when I look here, I've gone positive x, positive y to get to this randomly picked point on the unit circle. To get to this one over here, it would be negative x and positive y. So over here, my sine of this extra alpha here is the same as my sine of t. But my cosine of alpha and my cosine of t have an opposite relationship. One is the numeric opposite of the other, which we notate as saying, well, if I multiply by negative 1, then it's equal to the original. All right. And then likewise over here, with this angle they labeled beta, we could also label this angle negative t. So if I take my beta like the extra leftover distance there measures t, and that's just because of the way we've set up the two triangles here. You know, they share the same x distance over, so they must share the same y length measure, but whether it's positive or negative depends on which part of the unit circle we're looking at. So down here for this guy, if I take the sine of t, well, here, let's do the cosines first. So if I take the cosine of t, I get x. If I take the cosine of beta, I also get x. But beta is negative t. So this is telling me that the cosine of t equals the cosine of negative t. So when that happens, that's an even function. So this tells us cosine is even. And if we continued our original graph up here with the pink lines, like that would be my next graph. And then you can see, oh yeah, I fold that in half. Cool. And then our other trig function that only depends on cosine will follow suit, will be even. Now our sine over here, so remember our beta here I said was the same as negative t. So sine of t is the same as negative sine of negative t. So that matches our odd definition. And if you look back at the graph, if I continued and drew the same pattern, we're going to see I go up and then down, I go down and then up. If I took this graph and spun it about the origin 180 degrees, it would be all the same. All the points would line up. So sine is odd. Okay. So now looking at our unit circle, we see that certain trig functions are going to be positive or negative in certain quadrants. So the mnemonic device I learned in school was I draw my, X and Y axis like this. They are all positive in the first quadrant. And then just the same way you measure angles counterclockwise, I had all students take calculus. And there's a number of things you can come up with here. But what this tells us is sine is positive over here. Cosine is positive over here. Which means down here in quadrant 3, sine and cosine are both negative. And what we're going to see in 2.3 is that tangent is the quotient of those two. So the tangent, a negative divided by a negative, will be positive. And then our other three trig functions are the reciprocals of those three. So you have to get the association with those down, but you will have it on your formula sheet for the test. So this is more about remembering what to do when, not remembering all of the little detail number crunch kind of stuff. Okay. So a reference angle. We're going to make use of this whenever we're talking about something because the reference angle is going to be an angle measure between 0 and pi over 2. Remember I told you to memorize that first quadrant? That's all of our associations for 0 to pi over 2. So once I pick up the reference angle, that tells me the lengths of the sides, and then I just have to check what quadrant I'm in to know what do I make negative, what do I make positive. So this way, you're not memorizing the whole unit circle, you're observing all the cool patterns in the unit circle. So on each of these, like if T is in the first quadrant, then it is its own reference angle. If we move over to the second quadrant here, then our reference angle is the rest of whatever it takes to get to 180 degrees, a flat line. So I often look at that and I'm just thinking in my head, I'm like, all right, how much more to get to 180? That's my other angle measure. So T prime is 180 minus T. Now the annoying thing here is that they wrote T prime in the clockwise direction, so it looks like we would actually call it negative. Just ignore the direction of the arrows. Think of them more like double arrows saying, this arc measures. All right, and then same thing over here. Now these quadrant 3 I actually found a little bit nicer because I can see I go 180 degrees plus some. So if I just take off that 180 degrees, I have my reference angle for that little section in quadrant 3. And then quadrant 4, it's the whole circle minus the little wedge. So to figure out the little wedge, we take the big angle measure and subtract it off of 360 or 2 pi. So a lot of times I don't memorize these formulas. I draw a picture of, and I put the point where it's going to go. I draw my reference angle triangle and then work from there. So this is just more showing you where reference angles would be. And then on each of these, I can draw my vertical to make a right angle, make a right triangle for each of those. All right, so we're going to try some of this out. So this one is find the reference angle of 5 pi over 3. So our first step is to figure out where the heck is 5 pi over 3. So if I just look at 5/3, ignore the pi for a second. 5/3 as a decimal is 1.6 repeating. All right. So it's between 0 and 2, which is good. It is bigger than pi. Pi would be 3 pi over pi, and pi would be 3 pi over 3. This is 5 pi over 3, so it's clearly bigger than pi. So we are either in quadrant 3 or quadrant 4. The cutoff point for quadrant 3, that down spike 270 degrees, is 3 pi over 2, which 3 over 2 is 1.5. So when we're looking at our basic unit circle, this is 0 pi's, this is a half a pi, this is a whole pi, and this is 3/2 pi. So when I'm looking at my decimal here, 5/3, and then underneath the axis, I'm going to write the 2 pi. Just because it helps to kind of see the whole cycle finish out to a number. So where's 1.6? 1.6 is between 1.5 and 2. So that is where this angle is. I assume I could draw correctly. So there is 5 pi over 3. And I want to know what's the reference angle. So I drew this stick out here. I'm going to draw the vertical line always back to the x-axis. So all of our triangles, that vertical is always going back to the x-axis. All right, so I see I almost have a full circle here, or a full 2 pi. I just have this missing wedge. So my reference angle for this one is the whole circle minus the big giant angle measure 5 pi over 3. So a whole circle is 2 pi minus 5 pi over 3. 2 pi is 6 pi over 3 minus 5 pi over 3 equals just pi over 3. So pi over 3, larger fraction, that's the 60 degrees. 60 degrees. Now, if you look, like, my triangle honestly looks more like 45, 45, 90 than it does a 30, 60, 90. But when I get this reference angle, this is telling me that this angle measure here is pi over 3, or I'm going to write the 60 degrees. So 60 degrees is across from the longer side. So the length of this side over here is square root of 3 over 2. The length up here then, that's the short side, is 1/2. But since this triangle is in the fourth quadrant, the square root of 3 over 2, we went down to get there, so that has a negative value. So if I know the reference angle, I pull the x and y coordinates from quadrant 1, I look at where I drew it and figure out what's positive, what's negative for my x and my y, which is then the cosine and sine. So like here, we could have stopped at the pi over 3. Most of the time though, when you find a reference angle, like the next thing you're going to need to know is the sine and cosine. So my brain just like auto completes to that. All right, this guy, they actually give us a picture of 225, but 225 is between 180 and 270. Now looking at the degrees here, I can see that I have that is pi radians, or 180 degrees. And then I have a little bit extra. So if I take my angle measure, 225, and I subtract off the 180, I get 45. So all of our 45, 45, 90s, they're all square root of 2 over 2. You just have to check, is it going to be positive or negative? And in this one, all students take calculus. Tangent is positive, so the sine and cosine are negative. So both of these are negative. Not that it asked us to come up with the ordered pair, but once you know the reference angle, you know those distances, you're just checking what's positive and what's negative. All right, yeah, see? So use the reference angle to find the exact value of cosine of 150 and sine of 150. So if I draw my x and y, 150 is less than 180, but it's bigger than 90. So this guy is somewhere over here. Now I'm going to draw that vertical line so I can see my triangle. And the angle that I want to figure out is this bad boy here. Now if I look, that full to get to the line is 180 degrees. And I know this part of it is 150. So to get that reference angle, this is 180 minus 150. All right, so 30 degrees, the smallest angle is always across from the smallest side. So if you figure out where the 30 and 60 are and look opposite them, then you know where the smallest side is. So smallest side in a 30, 60, 90 is 1/2. This is the longer leg, square root of 3 over 2. But we have to check our coordinates. So I went left, so that is a negative x value. Then I went up, so the y value stays positive. So I have my reference angle, I have my triangle, I figured out the lengths, I figured out the sine. Then the last thing is just to answer which one's which. So if we go back to like SOHCAHTOA, sine is opposite over hypotenuse. So the opposite side, 1/2 will be our sine, and that corresponds to our y value, the vertical distance. So the sine of 150 is square root of 3 over 2. The cosine of 150 is negative 1/2. All right, now over here, 5 pi over 4. So when I think of this, like the first thing I do is kind of think about what's the nearest pi. So 5 over 4 is the same as 1.25, and you could just crunch that on the calculator. So that's pretty close to a single pi. Single pi is also 4 pi over 4, but it's less than 1.5 pi. So this angle is down here in quadrant 3. Now my reference angle is just that little wedge there. So I have my full angle measure. I've got an extra 180 degrees or pi radians on this thing before I can figure out what's the angle measure on the triangle. So I'm going to subtract off 180 degrees, which is pi radians. So 5 pi over 4 minus a pi. And I'm just going to be lazy and sneak the common denominator in there by multiplying by 4 over 4. And we get pi over 4. Pi over 4 is our 45 degrees. So our over 4 fraction matches our 45 degrees, and that is consistent. Pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4 all have 45 degrees, or pi over 4, as their reference angle. So this is the distances are square root of 2 over 2 and square root of 2 over 2. But both of those are negative because we're in quadrant 3. So the sine of 5 pi over 4 and the cosine of 5 pi over 4 is like that. They're both the same here. All right. So we're going to figure out where 315 is. That is bigger than 270. That is less than 360. It's also, if you look at the degree measure of those pi over 4 angles, pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4, all of the degree measures end in a 5. So you have 45 degrees, then when I add 90, I get 135. I add 90 again, I get 225. I add 90 again, I get 315. So, I mean, we knew just inspection and our knowledge that this measure was over in quadrant 4. So I have almost a full circle. So my leftovers to make the full complete circle is whatever I need to get total up to 360, which is another 45 degrees. All right, so we just figure out our coordinate pair, positive x, square root of 2 over 2, negative y though, so negative square root of 2 over 2. That's our cosine and our sine. The reference angle for negative pi over 6. So remember, negative angles, we start on that positive x-axis, but instead of going up, we go down. One second, it looks a little fun. Okay. So that is negative pi over 6. So if I started at the diagonal line and measured it up so it was positive, then it would be positive pi over 6. So either way, this is our 30-degree side. So this one up here is the 60. So on the right, we're going to go down negative 1/2 units. And we will go right positive square root of 3 over 2. So here's our cosine, here's our sine. All right, just 2 more. Find the coordinates of the point on the unit circle at the angle of 7 pi over 6. All right. So I've just been doing this on all of these because you do it a lot. So I know it's tedious, but the more practice you get at reasoning through this, the better your knowledge will be of the unit circle and of how to generate these things. You can do it a lot more quickly without stumbling and having to reference the unit circle all the time. But getting that comfortable requires practicing. So even once you get all the web work right, it might be a good idea just to go back and do a few, just to get more practice at it, get a little faster at it. So that way in calculus, you're not struggling to think through everything. You're like, oh yeah, I remember this. It's just like riding a bicycle. So 7 pi over 6 is a little bit bigger than 6 pi over 6, which is pi. So it's down here. Now, if you look at the unit circle, pi over 6, and then 5 pi over 6, 7 pi over 6, and 11 pi over 6, all 4 of those guys share the same reference angle. And that reference angle is pi over 6. So this one here is 7 pi over 6. If I draw in that little vertical line going back to the x-axis, if I take pi off of this, it's going to be pi over 6. And then our coordinate pair, pi over 6 is 30 degrees. 30 degrees is across from the shortest side. So this is a 1/2. Our long side is the square root of 3 over 2. But because we went left and down, both of those are negative. So the coordinates are negative square root of 3 over 2 and negative 1/2. All right, same thing here. In fact, I think I literally did this one earlier. Yeah, 5 pi over 3. So I'm not going to go through all of that explanation again for the same thing. But our reference angle is that pi over 3, which is 60 degrees. So across from that'll be the long side. So this one is short side, long side. So I cannot stress enough, practice until this gets comfortable. All right, I will record and upload 2.3 next.